explaining what they mean. So on that point, the computer science communities spent the last few decades developing more and more models of real-world artifacts. And so by real-world artifacts, I mean things like hardware or software that have been designed, developed and maintained by people who would more than likely describe themselves as engineers rather than computer scientists. And these artifacts have kind of messy edges. They've battled with economics, they've battled with the real world, and as a result, they're not often very well specified. And if they are specified at all, the specification may even be incorrect. So I'm talking about things like memory models of, say, the C programming language, processor architectures, language semantics, and so on. So we often spend a long time both developing these models, but also validating them, because we need to make sure, due to the lack of a proper specification, that they're correct. So by academic standards then, these projects are fairly large in that they involve multiple authors working across multiple sites, and they may take many man-years or postdoc years to build. But despite the fact that we're building more and more of these models, and despite the fact that we're expending so much energy and effort doing so, the engineering principles and the tooling that we have to build them hasn't caught up. The processes that we use to build these models are still quite rudimentary. So for example, it's quite typical to build such a model within the internal logic of a theorem prover like Isabelle or Coq. Or, to take an alternative approach, you could first build a prototype in a functional programming language like OCaml and Haskell, test that, do all your refactoring there, and then when you're sure it's correct, port it into the internal model of internal logic of a theorem prover. So usually this porting is done by hand, although there may be a degree of machine assistance there. But the machine assistance is often set or Perl scripts. There's nothing principled at all. Now, as a result, we argue that the community as a whole suffers from various ills. So most prominently, this translation from one language to another through the use of set or Perl scripts it could be error prone, and it's often ad hoc. The scripts are not reusable at all. They're specialized to the particular model at hand. So another ill is that we also have what we call theorem prover lock-in, or a balkanization of the community, in that the Isabelle people build their models, the Coq people build their models, the Hull 4 people build their models, and so on. And nobody can reuse the models of another community because the effort of porting models between the theorem provers is so high. So for instance, on this point, before I came here, we counted that there's 6 or 7 partial or fully specified x86 models in the literature. So another ill as well is when you're trying to port models between systems, you have to be quite an expert in both systems, and it's quite rare for people to be, say, an expert in Isabelle and an expert in PBS or whatever. Now, as a direct result of these ills, there's no library of off-the-shelf components. So if you're, say, building a verified C compiler, you can't just take, say, an ARM model or a PowerPC model off the shelf and reuse it. So often the very first thing that you do when you're building a verified compiler, or you're interested in program logics or whatever, is you build a model of a microprocessor, or your target microprocessor. Now, as a result of this, there's small fragments of models produced. People only produce the fragment of the particular microprocessor that they're interested in. So, for example, the Concert project modeled PowerPC, but it didn't produce a full model of the PowerPC architecture. It only modeled the instructions that the compiler would output. And often as well, there's not much validation done, because people are more interested in getting to the interesting parts for them, the actual verified compiler, rather than dwelling on building another x86 ARM or power model. So as an example, this is the C++11 relaxed memory model by Mark Batty, Yasmin Blanchette, and Scott Owens and co. This was developed 2010, 2011, and so this is kind of a flow graph of the process that was used to port between systems. Sorry, get rid of that. Oh, okay. So we started out with a model in Isabelle of the memory model. So atomic.theory was the model itself. And this was accompanied by another theory called code.theory, which contained a list of code equations telling Isabelle how to extract that model to ML. And within Isabelle, there was experiments done executing the model to kind of validate using the simplification engine as an execution system. And also there was experiments using nitpick, and quick check, which are like counterexample generators to make sure that the model was well, accurate. After that, they used the Isabelle code extraction from the code.theory code equations to produce some extracted ML files and did further validation there. And of course, there's backwards arrows going back from nitpick and from the extracted ML files back to atomic.theory where the model needed updating. And then with the extracted ML files, they linked in handwritten ML files to produce the CPP mem tool, which is a tool that can be used to step through the model by users and explain what's going on in real C programs. Now, sometime later, the team decided they wanted to do some proof using this model. But the person who wanted to do the proof was not an Isabelle user. He was a Hall 4 user. He was a Hall 4 expert. And also, the team decided that they wanted to speak to external people, say standards bodies, implementers, and so on. And for that, they needed LaTeX output. Now, Isabelle is capable of producing LaTeX output, but the system is optimized towards producing papers that you write inside Isabelle, and it wasn't flexible enough for what the team wanted. So what they did was produce a small tool called ISA2HOL, which parsed kind of roughly an Isabelle theory, or the Isabelle theories that they had. And so this produced something that kind of looked like HOL, but it wasn't HOL. So there was another script after that, written in SED, that took that and produced something that was a closer approximation to HOL. And then finally, they got close enough to HOL syntax itself that they were able to run HOL-doc and get a LaTeX output for for communication with outside vendors and experts. But of course, that leaves the proof side. So there was another SED script which took the output for ISA2HOL and eventually produced HOL theories, wherein the team was able to do some program proof using the HOL 4 system. So we argue that this flowchart is quite complicated. It's not at all optimal, and there should be a better way of moving your model that you've spent much time and effort on from one system to another. And what's really wanted is something like this. So you want some system, some machine, a piece of software represented here by the carding machine that will take a single input source description of your model, rip through it and produce, say, output in like an Isabelle theory or a Coq theory for reasoning with, ML or Haskell files for executing the model and validating and linking with external libraries to produce tools. Sorry. And also produce HTML and LaTeX documents for communicating with, say, standards bodies or companies, and so on. So with that in mind, we have a problem statement. So can we increase the amount of model reuse? Can we move to a situation where we write models once and then able to prove in any system that we choose. But can we make it easier and faster to build models of real-world systems? So can we move to a situation where people don't need to be an expert in Coq or don't need to be an expert in Isabelle to build models of, say, microprocessors? So that problem statement itself raises a number of other questions. So for any solution, what should be the input? What should it look like? What should be the syntactical language features, and so on? What backends do we need? So what other pieces of software will we extract to? And of course, any solution to these questions is going to be motivated by the models that we already write. And we have quite a lot of models at Cambridge, so we can use these to kind of gain some insight into what sort of a language we need. So I'm now going to examine quickly 3 existing models. Some of them predate LEM, our solution, and some of them have grown with LEM and influenced it along the way. And I'm going to identify some key characteristics that they all share, which will motivate some of the design decisions that we made in LEM. So the first model that I'm going to talk about is the Power and ARM operational model of relaxed memory behavior, which was by Sarkar and Go. And this consists of 2 components. There's a multiprocessor memory subsystem and a thread semantics. And these 2 components are specified in 2 different styles. So the multiprocessor memory subsystem is specified as an abstract machine, which uses sets and relations built over lists of memory events. And the thread semantics is specified as a series of abstract syntax trees of assembly and micro-operations with a label transition system defined over them with an inductive relation. So a LaTeX version of this has been used to discuss the model with IBM engineers. An OCaml version has been used as the basis for the PPC mem tool, which is another tool that allows users to step through the model and explain what's going on. And Coq output has been used for some preliminary yet unpublished proofs. And the second model is the same model that I showed the flowchart on the slide a few slides back. The axiomatic model for the C and C++ 11 concurrency by Batty et al. This is modeled as predicates over candidate executions represented as sets of events. So this a LaTeX version of this has been used by the C++ ISO committee. In fact, it's been quite useful in informing them of the design space for C++ 11 concurrency. It's been used internally at ARM by the GCC team and Linux developers. And an OCaml and HTML version, as I said, has been used as the basis for the CPP mem tool. Hall4 extracted outputs has been used to verify and explore the meta theory of the model. And Isabelle and Coq versions have been used in experimental proofs. And the last model I'm going to examine is CakeML, which is a verified implementation of ML by Kumar and company. And again, this is specified using a mix of styles. So there's an inductively defined relation used for typing, language, and bytecode semantics. The compiler is specified as recursive functions in a typical functional programming style. And there's also use of partial functions within the model itself, which they've found quite useful apparently. And the Hall4 version has been used as the basis of proof of correctness for the compilation, for the compiler and the semantics. So with all those in mind, it seems that we need a language which is basically the core of a functional programming language. We have functions, algebraic data types, pattern matching, etc. And it seems that we want a typed language as well. Also, we want sets and relations, and the relations are possibly inductively defined. We'll also want a library of common data types, for example, lists, sets, finite maps, and so on. Because we're trying to speed up the amount of time needed to build a model, so we'd like to provide users with a big library. And we'd like to target multiple theorem provers. We don't want to lock our users into, say, only ever using Isabelle or Hol4 or Coq. We want to target multiple ones. And at least one functional programming language for validation and linking with other tools. And of course, we want to produce nice typeset output. So that's quite a common requirement. So here's Lem, our tool. And as mentioned, it takes in a single input source description of a model. And as outputs, it can produce Isabelle/Hol, Hol4 and Coq output for reasoning with. It can produce OCaml code for executing the model, testing, validation, linked with an external tool. And it can produce LaTeX and HTML outputs for documentation, writing papers, and communicating with external bodies. So Lem, the language, should be familiar to, well, basically everybody in here. The syntax is similar to OCaml. It's a strong statically typed language with top-level polymorphism. It has algebraic data types, pattern matching, records, recursive functions, and so on. It also has a simple type classing system for ad hoc polymorphism. Although when I say simple, it's a lot more simple than in Haskell. It's more akin to Isabelle's type classing system. In addition to the functional programming features, there's also a set of features intended for specification of models. So we have inductive relations, we have restricted and unrestricted quantification, we have set comprehensions, and so on. And we also allow users to write down lemma statements that should hold of the model, and assertion statements, which are then extracted into executable tests in the OCaml backend, or actual lemma statements in Isabelle, Coq, or Hol4. So I'd like to emphasize this point, that Lem is not an alternative foundation for mathematics. It's a pragmatic tool, and it will happily accept a lot of code that would ordinarily cause problems in tools like Coq or Isabelle. So for example, we allow partial functions. We allow recursive functions that may not terminate or be obviously terminating, which is quite a problem in systems like Isabelle or Coq. And we also allow non-strictly positive types and things of that nature. So there's the assumption that the user has some idea of what they're doing, and that some care needs to be done on the user's behalf. So this is some example code. As you can see, it's very similar to OCaml. We have local functions, tuples, it's implicitly typed, so you have type inference, you have pattern matching, and so on. We have library functions like list.any at the bottom. So we can run Lem on this code to produce some OCaml output. And not much changes here, but so obviously in the Coq output, you can't fit this, the equivalent on the slide, so I have to resort to the OCaml one. But some things have changed. So for example, list.any has been transformed to list.exists. The set membership test has been transformed to a call to psec.mem, and so on. And you'll note that there's also a concerted effort to try and preserve the look of the code. So white space is preserved to the best of our ability, which we found actually helps trying to debug problems in Lem itself, and comments will be preserved as well. So similarly, here's some more Lem input. This is a set comprehension which builds a set of pairs, taking pairs from the HB set, performing that test and keeping them if they satisfy it. And Lem will produce, as a side effect, a LaTeX file with a series of macros, with one macro corresponding to, say, one type or one function, which you can then use in your LaTeX paper or documentation, and you get something that looks quite nice. So the text-based for all has been changed to a universal quantifier, and so on. So there's a temptation to think that Lem is just doing string-to-string manipulation, but that isn't correct. Lem's actually working quite hard behind the scenes. So in particular, each backend has a different notion of primitive pattern. So some backends support as patterns, record patterns, and so on, but they all don't support the same set. So pattern compilation in LEM has to transform all of these away and stop when it reaches the primitive patterns in each backend to make sure that we are extracting idiomatic code. We also want to map various existing types in LEM to various types in LEM to existing types in each backend. So, for example, we want to map maybe and its constructors to option and its constructors in Isabelle and OCaml. And again, this is not just a string-to-string transformation. So, if you look at fold right, there's an amazing variety of argument orders between each backend, and you need to be able to reorder the arguments to be able to extract correctly. We also wish to allow inlining of definitions, and all this can be done on a per backend basis. So for Coq, you can inline a function, and in Hol you can map to an existing one, and in say OCaml you can extract a LEM version and use that. And also renaming is necessary. So one of our PhD students produced a model with a function called op that took an argument called op of type op, which produced a result of type op. And if you feed this naively to Isabelle, it just dies because op is a reserved name. So some cur has to be taken in renaming in each of the backends. And to do this, it has to have some knowledge of the backend namespaces. But we allow the user as well to override the automatic renaming and give explicit names to use. So the status of LEM, well, we think it's great. There's multiple large models been written in the system, and it's produced a lot of good papers. So we've got a lot of POPL, PLDI and CAF papers produced using it. We've got lots of memory models, say the Power, ARM, C and C++11 concurrency models. We've also got correctness of compilation schemes into those models. We've got TCP/IP specifications, and we've got various specifications of languages like OCaml Lite, and also the aforementioned KCML, with more being written now. And Reusable allows users to quickly start writing models. It has more the feel of a programming language rather than a theorem prover. However, LEM's type classes are still a bit too simple. They're single parameter, there's no constructor classes, so you can't hammer monads into LEM using them. And there's also no deriving of common instances of common type classes like EQ or odd. And also for Coq, the code generated is often not quite idiomatic. So admittedly, LEM is closer to the whole family systems, and in particular, the bool type in LEM causes a big problem for Coq, which doesn't identify a prop and bool like the whole family systems do. However, we're continuing to develop it. We're producing new ideas, and we're producing new solutions to those problems mentioned on the last slide. So the problem with bool in Coq can be fixed with a change to LEM's type system, for instance. We can split bool in half and have a prop and a bool. And the type classes can be generalized as well. The limiting factor here is basically manpower and time and money. And also we want to add more features, so it would be really nice if we had, say, a quick check system within LEM, so we could blast a model that we'd written with random values to see what properties it had. So to conclude, LEM is a pragmatic tool for engineering real-world semantic models. It's been used extensively within Cambridge, and it's now being adopted elsewhere. So yesterday I met our first external user in Munich who's using the KCML model in Isabelle. And it aims to break problems with theorem prover lock-in, balkanization, and helps make models more portable. We argue it's more lightweight than a theorem prover with the feel of a functional programming language. So thank you, and if you want to experiment with LEM, then you can go to Peter School's website where you can opt in.
Time for one question, maybe?
So you said this is not a good foundation for mathematics, but maybe it is. So maybe you can confirm my impression. We basically So So basically, the logic, it sounded like it's predicate logic over a functional language.
Yeah, it's an approximation. Yeah.
Yeah, beefed up with some nice features.
Yeah, it's basically whole. Yeah.
Because there is work on the foundation of mathematics, which basically takes that as the basis. You start with lambda calculus and you put predicate logic on top of it, and you have inductive relations as well. And this is a strong logic developed by people like Peter Axel and Tefferman.
Mm-hmm.
And you know how to model multiple type theory in such a language, for example. It's one of the standard models of multiple type theory. So it's actually very powerful and useful, I would say, language,
yeah.
which is both a logic and a programming language. And it's very striking how this has been missed by the community, by both the theorem proving community and by the functional language community, I think. Sorry? Yeah, exactly. So there are people who have used it, but it's never caught on in the same way as Reusable and Koch. I think there's never been a really good implementation, but it does appear now and then for decades, and you can go back decades for people having somehow brought up this idea.
Yeah.
But there is still no really good system doing this compared to Koch and Isabel.
Yeah, when I said that it's not an alternative foundation for mathematics, it was more of a signal of our intent and focus. So we're basically trying to solve a very practical problem that we have, in that we want to get rid of these set scripts and allow users to use our models that have been developed in Cambridge. And we're not really interested in building termination checkers and positivity checkers and so on that would be needed, for example, to make a proper system that acts as a foundation of mathematics.
But the point is that you actually don't need those things in a foundational system.
Okay.
You can build it on partial functions and calculus.
Okay.
Anyway, thank you.
All right, yeah, thank you.
Hello, Joachim Breiter from Karlsruhe. One thing that I always find annoying, or at least tedious, with formal models and theorem provers is naming and binding issues.
Yeah.
So do you support it anyway, or if I need that, am I still locked into a particular system?
So there has been some talk on trying to incorporate some nominal stuff into LAM. So we have Andy Pitts, who's ostensibly working on this. I don't know how much progress he's made. So yeah, it's being talked about, but there's nothing there at the moment. If you want to handle binding, then you have to use De Bruijn indices basically, or strings. Yeah.
Thank you.